Okay, so in this video I'll talk about adiabatic quantum computation, which is a very interesting way of organizing a quantum computer, very different from the circuit model that we've been looking at so far. So let's see the motivation for this. So we already saw that if you want to look for a needle in a haystack by doing unstructured search, then if the table is of size n, any quantum algorithm must take square root of n steps. Okay, but this is in this model where the function f is given to you in the form of a circuit like this, and all you're allowed to do is make queries in superposition, but you're never allowed to look inside this box to see how f is actually being computed. So you could ask, well, does this necessarily mean that quantum computers cannot solve NP-complete problems in polynomial time? Because after all, square root of n, if n was 2 to the little n is the length of the input, and square root of capital N is 2 to the little of n over 2. So must you take exponential time even on a quantum computer? Well, the answer is no, it does not necessarily follow. What does follow is that any quantum algorithm that does better than 2 to the n over 2 steps must use the structure of the problem. It must look inside the box that's computing u sub f and actually rely on the structure of f. So now there was a great deal of excitement about a decade ago when there was this paper published in Science which gave the framework of adiabatic quantum optimization, this new type of algorithm, and then they ran simulations on small examples of NP-complete problems, like 3-SAT, and showed that this particular algorithm, this particular way of implementing quantum computation, seemed to solve 3-SAT in polynomial time. So the algorithm was too complicated for them to analyze, but the simulations on small instances, of size n equal to 10 and 11, 15 maybe, seemed to show that it ran in polynomial time. Okay, so what's this adiabatic quantum optimization? Now, this is going to be a little fast for many of you. So follow what you can. Hopefully it's useful for some of you, but maybe for others it'll just give a sort of a feel for the subject. It'll give you a little bit of an outline of what it looks like. Okay, so here's how adiabatic optimization works. So we specify in adiabatic optimization the Hamiltonian that's working on the qubit. So we have a system of n qubits, and we have a Hamiltonian h0 acting on it. And moreover, we set up the n qubits in the ground state psi naught of this Hamiltonian. So we know the ground state of h0, and we set up the qubits in the ground state. Then what we do is we gradually transform h0 to a new Hamiltonian h sub f. Okay, so h0 is the initial Hamiltonian, h sub f, final Hamiltonian. And how do we transform it? We write it as convex combination of h0 and h sub f, and we gradually increase t from 0 to 1. So we have a dial, and we gradually turn it until we get to h sub f. Now, the ground state of h sub f is phi sub f, and this is unknown. And moreover, we set it up so that finding this ground state is exactly the problem that we are trying to solve. So now, there's a theorem called the quantum adiabatic theorem, which says that if you do this transformation slowly enough, then you actually track the ground state. Meaning, at any given time, if your Hamiltonian is h sub t, then you're always in the ground state of your instantaneous Hamiltonian. So you start in the ground state, and you stay in the ground state as you change the Hamiltonian, so you end up in the ground state of h sub f. So that's your algorithm. That's the new kind of quantum algorithm. It just does this, it drags the ground state along. The only question is, how fast can you go? Well, the limit in the adiabatic theorem is that the total time that you take must scale as 1 over the square of the gap, of the spectral gap. What's g of t? Well, g of t is the difference between the two smallest eigenvalues of h of t. So it's the difference between the ground energy and the first excited energy. It's a gap between the two energies. And so you find the time when this gap becomes the smallest and you take 1 over the square of that gap. Okay, now let me very quickly say how you would actually write a Hamiltonian corresponding to, say, satisfiability, 3 satisfiability. So remember, in 3 satisfiability, you have n bits, so you transform them to n qubits. You have clauses which look like x1 or x2 or x3. It says either x1 is true, or x2 is true, or x3 is true, meaning either x1 is 1, or x2 is 1, or x3 is 1. So that corresponds to a Hamiltonian that acts on the first 3 qubits, and it acts like this. This is what the Hamiltonian looks like. It's an 8 by 8 matrix, and it assigns a penalty, an energy penalty of 1, if this clause is not satisfied. So the only assignment that fails to satisfy the clause is 0, 0, 0, and so you assign a penalty of 1 there, and zeros otherwise. Okay, so now, and your Hamiltonian H is just your H is just going to be H1 plus H2 plus H sub m. So you just have the corresponding terms. And now, where each of these H sub i's acts non-trivially only on the 3 qubits, and it acts as the identity everywhere else. So your satisfying assignment does not get an energy penalty on any of these clauses, on any of the terms of the Hamiltonian. So it's an eigenvector with eigenvalue 0, so the ground energy is 0. But any arbitrary truth assignment is an eigenvector with eigenvalue equal to the number of unsatisfied clauses. So the way you can solve satisfiability is just look at that ground state and see whether it satisfies all the clauses or not. Okay, but how fast can you go? Well, as we saw, the total time that this algorithm must take is 1 over the square of the minimum gap. Here's what we know about it. On the one hand, we know that if you just using the adiabatic quantum algorithm alone, you can get this quadratic speedup for unstructured search, meaning you can recover Grover's algorithm, but without even having to design the algorithm. All you do is use the adiabatic algorithm with suitable parameters, and you do the analysis, and it already works. But on the other hand, it can also be shown that in general, the gap can get exponentially small, and so you need exponential time. Actually, there are also, this paper here shows that the gap can get exponentially small even for NP-complete problems, even for very, very simple NP-complete problems, even for instances of 2-SAT, or of SAT when the variables are placed in a one-dimensional line with nearest neighbor interactions. On the other hand, this paper also shows that the adiabatic algorithm can tunnel through local optima in certain special circumstances. Now, the news for the adiabatic algorithm became somewhat even more pessimistic with this more recent paper, which shows that, in fact, it gets typically stuck in local optima. Nevertheless, the company D-Wave that this article talked about has actually gone ahead and implemented this kind of adiabatic quantum computation. And in fact, last year, they sold their first such quantum computer for $10 million. So how to think about this? Well, let me just give you a way to think about this. So what does adiabatic quantum computing do for you? Why should one still persist with it, even though it doesn't, it obviously, there are lots of indications that it does not give you this exponential speed up that we are looking for. Well, here's the best case one can make for going forward with it. So the best case is, well, we know that in general, this algorithm does not solve NP-complete problems in polynomial time. It does not give an exponential speed up. But we could still hope that on the typical instances, on the kinds of instances of satisfiability or of some other NP-complete problem that we care to solve in practice, that this technique gives a speed up. Now, the other advantage of adiabatic quantum computation is in decoherence. So this is something that we haven't talked about yet, but quantum bits are very fragile, and you see when you measure them, then the quantum state collapses. But this measurement can happen not because we want to measure it, but just because the environment happened to be looking in. And so in order to do quantum computation, you've got to protect the qubits from the environment. And this is a difficult task. So in the case of adiabatic quantum computation, you actually have a Hamiltonian, and that's acting on these qubits, and the qubits are in the ground state. So intuitively, you can think of it like this, that the Hamiltonian is holding on to the state of these qubits, that they are in the preferred state. And so the environment has a harder time measuring the state of these qubits and getting the qubits out of the grasp of the Hamiltonian. So that makes it easier in some sense to implement this kind of computation without actually implementing the kind of fault tolerance one would need. On the other hand, there are a lot of problems with the approach, including the fact that it's easy for the Hamiltonian to hold on to these quantum bits when the spectral gap is large, when the energy gap between the ground state and the excited state is large. But when the energy gap falls down, when it narrows down, then it's very hard for the Hamiltonian to hold on to these qubits. And so that's where the problems arise, and that's where the results seem to indicate that the gaps get exponentially small. And so my opinion is that it's very unlikely that this approach really works. On the other hand, if it does work, that would be a remarkable thing. So this is the kind of thing where somebody clearly should be performing the experiments, and it's a good thing D-Wave is. The bad part of it is D-Wave is a commercial company, and so they need to hype up their results in order to say they are doing something worthwhile. And that's where the problem arises. That's where these kinds of headlines come up, which say, well, they've created the first practical quantum computer. As you can see, Scott Aronson, who is now a professor at MIT, he was my former student. I think his quote in this article is very, very apropos, where he says, there's an enormous gap between demonstrating the kind of quantum effect in 8 qubits, as they've done here, and saying that they have a 128 qubit chip that can perform a computationally interesting task faster than a quantum computer. So there's a lot of skepticism that this so-called quantum computer can do anything interesting yet.